All right, so we have this bungee cord problem, and we should be clear on what's going on, what we're calculating, and what all of this is in fact about. So, to this end, let's just go ahead and calculate a couple things that, or actually, even before we calculate anything, I just want to label some things. So, whenever I see these bungee cord problems, I'm just tempted to think about energy. Okay, so what I want to kind of do is talk about what different energies are happening here. So, as I work here, I've got a platform apparently, and I see that I have gravitational energy here and here and here. Here it's at a minimum. What else do I have? It seems that I'm getting a little bit of kinetic energy, kinetic energy. So I'm looking at the overall structure of this thing. I'm going to tell you right now, I am seeing this looking like an energy problem. So what I want to do is, this time I'm actually going to go straight for the data booklet. Okay? I'm going to get some data booklet equations here. Okay? Maybe it's useful, maybe it's not. Let's just get it written down. So I'm going to say EP is mg h e k is 1/2 mv squared. And let's get that elastic one in there. It's 1/2 k times the stretching squared. Okay? And let's remember that k is the spring constant. That's whether the spring is stretchy or not. Like car shocks have really big k's and slinkies have really small k's. It's kind of where we're at with this. So we have young Joanna doing a bungee jump, and we want to see what happens to the energy. So let's just go ahead and actually track this. So from the platform to A, our gravitation, well, every time we get lower and lower, our gravitational energy decreases. So here we are decreasing. Okay, we're decreasing all the way down. So here, here, and here. Okay, all decreasing. Now, from the platform to A, clearly our kinetic energies increasing, and because we're falling and we're gaining speed. Now, this final equilibrium position, let's be clear. When we say equilibrium position, let's be clear. This is where forces balance. Let me make one more point there. I should have written that in orange before. Equilibrium position means forces balance. Let's be clear on the forces that are balancing. Here, this is the weight force is actually balancing the spring force. I'm going to just use absolute value sign so that we're clear on notation. In other words, right here, imagine this bungee cord attached to the person. So we've got the spring force up and the weight force down, and they balance each other. Okay? So with this in mind, as we're falling, we actually gain speed until the force is balanced. What we're basically saying is that the gravity force is bigger than the spring force and so continues to accelerate it. So that means we're going to have an increasing kinetic energy. And then we go from B to C, where we pass the equilibrium point, and now the spring force is bigger than the gravity force, and it's going to start to slow the jumper down. Now, as far as the elastic potential energy goes, from 0 to A, there's no stretching of the cord, so nothing happens. And then as we continue to stretch more and more, we are just going to continue to increase our elastic potential energy the whole time until we stop. All right. Now, it says here, estimate Joanna's vertical speed at point A, the point where the bungee cord just starts to stretch. So let's be clear. We've got E at the platform, the total E at the platform, equals E at beginning to stretch because I suck and can't come up with a better beginning to stretch. I can't think of a better way to say it. So what does that mean? We have all gravity, and that becomes all kinetic. So let's be clear. This is all E potential due to gravity, and this is all E kinetic here. So her mass actually cancels. So 2gh equals v. The h through which she falls is, let's be really clear, this is obnoxious. They do a really annoying trick here, okay? And I forgot to say this. So, it says Joanna's center of mass is 1 meter above her feet. That is so annoying. What we're basically saying is that Joanna is here. So her height starts off as 1 meter above her feet, but then she's upside down here. Okay? So we have 1 meter below here. So this distance here is 25. This is so annoying. This is 1/2. So 2gh equals v. h is going to be 2 times 10 times, so annoying, 27 for v under the square root. You need the 25 you fall plus these extra 2 meters, which is just, it's just a stupid gotcha question. I can't believe they would do that. So when we actually get that, actually I can. We're going to end up getting here about 23. Let's see, how many sig figs? Take it out to 3 sig figs. All right, so we're going to get 23.2 meters per second. Now, we want the resultant force acting on Joanna when she's at her lowest point. So let's be clear. The net force, well, let's look at her at the lowest point. She's got the spring force going up, the gravity force going down. So that's going to be spring minus gravity, and that's going to be K times the stretching distance minus her weight. The stretching distance is going to be the 45 minus the 25 from the equilibrium, okay, minus her weight. Now we were told the K above is 75, so that's going to be 75 times 20 minus 540, and that ends up being about 1,500 minus 540. I think it's like 960. Yeah, 960 newtons. Okay, now it says here, after reaching the lowest point, the stretch bungee cord accelerates Joanna upwards, and this way she bounces up and down a few times before stopping, hanging by her ankles at the end of the cord. This is a trick question. How much is the cord stretched when she's in this final position? Again, the idea here is we just want to know the stretching of the cord at the very end when she is basically done with this whole process. So that's going to be F net is going to be 0. K delta X equals mg. So that's 75 times delta X equals Joanna's weight of 540. So delta X is going to end up being 72 meters. So that's it for the bungee cord problem.